Extreme physics.
All right, here's the energy test. If you click on the question, you can jump right to the ones you're interested in. Question number 1, a spring gains 2.34 joules of elastic potential energy as it's compressed 0.250 meters from its equilibrium position. What is the spring constant of the spring? All right, we have a spring. Here's its equilibrium position. I'll call that 0. And it gets compressed. I don't know why it got compressed. Let's say that we put a block on top of it. So it got compressed this distance. We call that x. When you compress that, it gained a potential energy of 0.234 joules, and it got compressed. This x value is 0.250 meters. What is the spring constant, K? All right, well, we could try Hooke's law, F equals Kx, but we can't use that because we don't know what F is, all right? So we could take a look and we could say, well, the potential energy in the spring equals 1/2 Kx squared. Well, we know the potential energy and we know X, so we could calculate K. Don't forget to square that X. 74.9 joules stored in the spring, and whatever choice that was. On test A, that was choice 4. Mala! All right. An ideal pendulum is released from position A. All right, so it looks like it's at rest at A and swings freely to B. It looks like it's going to be at rest at B too, and then it's going to come back. As the pendulum swings from A to B, what happens to its total mechanical energy? All right, we need to know what total mechanical energy is, and total mechanical energy is E. Mechanical is an object's potential plus kinetic energies. Right. As the pendulum swings, these remain constant. So the choice is 4. Certainly, as it swung down, the potential energy would drop and the kinetic energy would go up until it gets to the bottom. There we had this. Energy pi! Energy pi. We had all gravitational potential energy. Here, same size pi, all kinetic energy. I'll try and draw them the same size. And all gravitational potential energy. And if it was somewhere in between, it would have a combination. But the pi would remain constant in size because energy is conserved. And in a system like this, mechanical energy is conserved. If a motor lifts a 400 kilogram mass a vertical distance of 8 meters, what is the minimum power generated by the motor? Power is the rate at which something does work or expends energy or somehow uses or creates energy. So power is work divided by time. And if you're lifting a 400 kilogram mass, here's the mass. 400 kilograms. All right. How high does it get lifted? 10 meters. All right, it gets lifted 10 meters. Here's our mass. 400 kilograms still. Mass doesn't change. 10 meters. All right, all the work I did became gravitational potential energy. Why don't I just calculate the gravitational potential energy here? That is going to be mg delta H is going to be the work. And how long did it take? 8 seconds. So let's just bring all this stuff up here. So the choice was, and they had it in scientific notation, 4.9 times 10 to the 3 watts. Which graph represents the relationship between kinetic energy and speed for an object falling? All right, well, graph. Kinetic energy and speed anytime you graph something. First step, find the mathematical relationship between kinetic energy and speed. Ooh, let's apply extreme physics. Well, our x variable is v, and our y variable is kinetic energy. When v is extremely small, or 0, the kinetic energy is 0. When the velocity is big, extremely big, the kinetic energy is big. All right, 0, 0 is right here. Big, big is right here. Well, that's not linear. That's not linear. We're not linear about that. This is squared. This is a curve. This is looks like that. That was choice 3 in this. Like that. Determine the work done by a 30.4 Newton force in sliding the crate up the incline. Well, work is force times displacement, but the force and the displacement have to be in the same direction. Let's see, are they? Looking at that, yes they are. The force and the displacement are in the same direction. Sometimes, as a reminder, I put a cosine of theta there. Theta, of course, is not the direction relative to the horizontal. The force relative to the displacement. Well, the force is this way, and the displacement is that way, so the angle between them is 0. So this is 1, not 1. All right, so this is just force times displacement, because they're in the same direction. That's the idea. The force and the displacement have to be in the same direction. 182 joules. Calculate the total increase in gravitational potential energy. It's going 6 meters this way, but the gravitational potential energy is determined by how high you go. And that was 3 meters. All right. Change in gravitational potential energy is mg delta h. All right, let's see how much it increases. mg, of course, is 40 newtons. This is the weight. That's the weight of the object. They gave us the weight. You need to recognize that. And you should have saw that was 40 newtons. 40 newtons. Don't take the weight and determine the mass and then multiply by g again to get the weight again. You're going to lose points if, when you do that, you have too much rounding error and you get the wrong number. 120 joules. All right, if you didn't get that answer, some of you calculated the mass and you came up with a number that was like 121 or something like that, and that wasn't correct. It's 120. You need to recognize when you see mg, that is weight, right? That is weight. So that was the potential energy. Number 7, what happens to the kinetic energy as it goes along the incline? If you read the question carefully, it says it goes at constant speed. So the kinetic energy remains the same. Kinetic energy remains the same because they clearly said at a constant speed. Constant speed. All right. State what happens to the internal energy as it slides along the incline. That's point 0. That's point 1. The energy at 0 equals the energy at 1. Let's see what kind of energies we had in this case. Well, we started off, we had kinetic energy because they said it was moving at a constant speed the whole time. And I'm going to call the bottom 0. I'm going to say potential energy is 0 at the bottom. So it doesn't have gravitational potential energy. It doesn't have spring potential energy because there's no spring involved. So the kinetic energy at 0 equals the potential. It also has kinetic energy at 1, right? Because they said it was moving. And it has gravitational potential energy at 1. And is there internal energy? Sure there is. Sure there is. There is internal energy because this isn't a frictionless surface. There must be friction. And we forgot to add the one other thing. During this whole time, some work was done, right? So there's our energy equation. State what happens to the internal energy. The internal energy increases. Internal energy in these problems never goes down. Now, the kinetic energy at 0 equals the kinetic energy at 1, so that's going to drop out. So the work that you did in pushing this up the ramp is going to result in potential energy and internal energy. And you would see that the work you did was more than the potential energy. You should have saw that in steps 1 and 2. In fact, the work you did was, this work right here is 158 joules equals the potential energy, which was 120 joules. They don't match because there was internal energy. All right. And that was the difference between those, but they didn't ask you to calculate that. That would be easy to do, though. Number 9. How much work is done in lifting a 0.1 kilogram hamburger vertically upward at a constant velocity, 0.3 meters from the table? How much work is done? Any work? Work always increases the energy of the system. So the work that was done is going to become gravitational potential energy in this case. So the work really is just going to equals a force times displacement. Or in this case, the work is going to equal the gravitational potential energy. We could look at it like this. Here's our burger, and it's lifted 0.3 meters. All right, well, we could look at this from the conservation of energy standpoint, and we could say this is 0 and this is 1. Potential energy here is 0 at this height. It doesn't start out with gravitational potential energy. It starts off with kinetic energy. So it's moving at constant velocity. Kinetic energy at 0 plus no gravitational energy, no gravitational potential energy, plus the work done equals the kinetic energy at 1, but they said it's lifted at constant velocity, so that's going to be the same, plus the potential energy at 0. Well, these are going to equal each other, so since the kinetic energy at 0 equals the kinetic energy at 1, you can subtract those out, and they go away, because it's the same number. So the work done is going to equal the potential energy, gravitational potential energy. Let's put a G there. And that is going to be mgh. They only gave us one significant figure here, so it's looking like 0.3 joules. All right, a watt second. A watt second is a unit of what? So we have a watt and we have a second. Second is a measurement of time, and watt, if you didn't remember what a watt was a measurement of, you could look earlier in the test and they said the power of something was in watts. So this is power and this is time. So what is power times time? All right, well, what is power? Power is energy divided by time. So therefore, power times time must equal energy. The choice was 2. If you recognize the watt as a unit of power, then you must know that a watt second can't be power, because a watt is power. If a unit represents a quantity, if you multiply it by something else, it must represent something else. So if a watt is power, a watt second can't be power. It must be something else. Which quantity has both magnitude and direction? So we're looking for vectors. The only one in there, energy is not a vector. Work isn't. I mean, energy is a scalar, right? That's what makes it nice and easy to work with. It's a scalar. So energy, work, and power is energy divided by time. So that's a scalar too. Impulse. Impulse is a vector. And the direction of the impulse is in the direction of the net force on the object. All right. So the answer there was impulse. Choice 2. impulse. Two elevators, A and B. They move at constant speed. Both of them move at constant speed. Elevator B moves twice the speed of elevator A. All right, so let's see. We have V of A and V of B equals 2 times V of A. Ooh, interesting. Elevator B weighs, all right, so we have force of gravity A, and it says elevator B weighs twice as much. So the force of gravity on B equals twice the force of gravity of A. Huh? It's getting very intriguing at this point. I wonder where they're going with this. Compared to the power to lift A, compared to the power lifted to A, we want to compare that to B. All right. Well, what is power? Power is work divided by time, or energy divided by time. Or it's force times velocity. Get that in your reference table. Force times velocity. In this case, the force is the force of gravity. All right? It's going at constant speed. So we have the force of tension pulling up, force of gravity down. If it's a constant speed, they must be equal. Did I draw them equal? No, I drew the force of gravity bigger. Let's draw them equal. There, that's equal. Right there. Equal. All right. They must be equal if it's moving at constant speed. So power of A equals force of gravity of A and the velocity of A. Let's see what the power of B is. The power of B is force of gravity on B times velocity of B. Let's see. Force of gravity on B is 2 times the force of gravity of A. Velocity of B is 2 times the velocity of A. So that looks like it's 4 times GA VA. But FGA VA is 4 times power of A. Let's see, is that a choice? Yes, that's 4. 4 times is great. 4 times is great. What is the maximum height in which a motor having a power rating of 20.4 watts can lift a 5-kilogram stone? Yes. The Board of Regents is getting creative on this one. A motor is lifting a stone vertically in 10 seconds. What maximum height can this? So we know that power is energy divided by time. We have the power and the time, and let's see. And the energy it takes to lift this is going to turn into gravitational potential energy. So I could say, oh, this is gravitational potential energy divided by time. That's the energy right there. Oh, it looks like we have everything to solve this. This is fantastic. Yep. All right, let's plug away. What choice is that? 3. Power is energy divided by time. The amount of energy it expends gets converted into gravitational potential energy divided by time. What is the total amount of kinetic energy that the mass has as it swings through its equilibrium position? All right. Mechanical energy is clearly conserved here at B. They want to know the kinetic energy at C. Kinetic energy at C equals what? Potential energy at A, the gravitational potential energy at A must equal the kinetic energy at C. mgh of A equals the kinetic energy at C. Kinetic energy at C equals 110 joules. And that is, of course, also the potential energy at A. So that's choice 3, I guess.
A student produced various elongation of the spring by applying a series of forces to the spring. The graph below represents the relationship between the applied force and the elongation in the spring.
That looks remarkably like a lab. What is the spring constant of the spring? It is the slope of that graph. And we had force versus elongation. They use x for elongation. This is the equation of a straight line. Y equals the slope. The slope is the spring constant, which is k, x. That's Hooke's law. Since it goes through the origin, we can use 0, 0 as a point, so we don't necessarily have to, in this case, calculate the slope, we can just say the spring constant is F over X. Pick any point. I will choose 20 newtons per meter is the spring constant. Spring constant is 20 newtons per meter. Calculate the energy stored when it's elongated 0.3 meters. The potential energy in the spring is the area under the graph, right here, or 1/2 kx squared. You could have used 1/2 kx squared, 1/2 kx squared, use that, or it's the area under the graph, so I'm going to use that instead. We'll get the same answer. 1/2 base times height. Base is 0.30 meters. Height is 6 newtons. We're taking the integral. We're doing calculus, aren't we? Fancy pants math people. 0.90 joules. Make sure you have at least 2 significant figures. Everything in here had 2 significant figures. Make sure you have 2 significant figures. Don't give me that. No, no, no. No, 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 no. No, 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 no. Question 17.
A wound spring provides the energy to propel a toy car across a level floor. At time ti, the car is moving at speed vi across the floor, and the spring is unwinding.
As shown below.
At time tf, the spring is fully unwound, and the car has coasted to a stop.
All right. Which statement best describes the transformations of energy that occurred? Well, what kind of energy did we have here? In the beginning, we had a spring there. All right, we had, let's see, do we have gravitational potential energy? Nope. Nope. No. Do we have spring potential energy? Yes. Yes. Do we have kinetic energy? Yes, because it says it's going initially. Is external work being done between here 0 and 1 when it stops? No, there isn't. Okay, the work was done before 0 when you were winding it up. So there is none of that. And here, no gravitational potential energy, no spring potential energy, no kinetic energy because it stopped. But there is internal energy. It heated up the floor a little bit, and it heated up the wheels a little bit, and some other stuff, maybe some gears and stuff. And so the answer is gravitational potential energy at Ti. No, it doesn't have any, so it's not 1. 2, elastic potential energy at Ti. Yes, it does have elastic potential energy. Is converted into kinetic energy at T final. Well, it doesn't have any kinetic energy at T final. Both elastic potential energy and kinetic energy are converted into internal. Yeah, that looks like it. Okay? These two end up like that. We had our energy pi. We had spring potential energy, and we had kinetic energy. I don't know what the ratio was, but we had both of those. And same size pi, but all we have left is Q. Looks like that's the answer. What's wrong with 4? Both kinetic energy and internal energy are converted into elastic potential. I don't know, it just doesn't make any sense. So, all right, so the choice was 3. The Sledder shown starts from the top of a frictionless hill. Ooh, no internal energy. Of height h0 and slides into the valley. What initial speed v0 does the Sledder need to just make it over the next hill? What do they mean by just make it over the next hill? What do they mean? They mean something. They didn't say make it over the next hill. They said just make it. So basically, when it gets there, it basically has no speed. Okay? So the kinetic energy at the end is going to be 0. Let's see how we do this problem. Well, just to get it over here. So essentially, they have 0 velocity there. That's what they're saying. To just make it over. All right. H0. H1. Let's set up our equation. What kind of energy does it have? Well, it has kinetic energy. Certainly it's moving. It has gravitational potential energy. Well, maybe it does. I will call the gravitational potential energy 0 at the bottom, so then it does have gravitational potential energy here. All right? Let's see. There's no springs, no spring potential energy, and no work is being done. No one's pushing this sledder during the problem, so it is, here we go. So there is no work being done. Equals the kinetic energy at 1, which is 0. Okay, V equals 0 here. So there's no kinetic energy. We only have gravitational potential energy at 1. And there is no Q because there's no friction. So we want to know how fast is the person going. So let's say 1/2 mv0 squared plus mgh at 0 equals mgh at 1. The masses go away. Nice. How fast is it going at 0? V0 looks like it is. Your answer should be in terms of the values given and fundamental physical constants. Let's see. G is a fundamental physical constant. 2 is a number. Number 0 is okay. H1 and H0 are numbers given. That looks like that's our answer. If you put a value for V1 in there, you lost a point. Because you needed to use your judgment when it said, how fast does this need to be going just to make it over the hill? If you included V1, then you've ignored the just part. All right, if you have any other questions, come see me at school. Bye-bye.
Extreme Feather.